We've seen that Taylor series can be really useful to help us approximate complicated functions using polynomials. Here we're going to examine 6 important Taylor series. For each, we'll come up with a formula for the Taylor series centered at 0, otherwise known as the Maclaurin series. We'll establish its interval of convergence using the ratio test, and we'll explore whether or not the series is equal to the function for all of the values on its interval of convergence. Let's start with establishing the series for e to the x centered at 0. So we can see it given here, but let's go ahead and work through it. So we have f of x is e to the x, and our a value is going to be 0. We need to look at some derivatives, but of course, f to the n, the nth derivative of e to the x, is just e to the x. For any n, this is its own derivative, which means that f to the n of 0 is e to the 0, which is 1. So it can be pretty quick to establish that our Taylor polynomial is going to be the sum from n equals 0 to infinity of f to the n of 0, so 1 divided by n factorial times x to the n. And I used n here instead of k, but obviously those formulas are exactly the same. So we have x to the n over n factorial. Our next order of business is to establish the radius of convergence for this. So we're going to use the ratio test. We're going to look at the limit as n goes to infinity of the absolute value of x to the n plus 1 divided by n plus 1 factorial, all over x to the n over n factorial, which means we can multiply by the reciprocal, n factorial over x to the n. We'll move some terms around there. So we have x to the n plus 1 over x to the n factorial over n plus 1 factorial. And then using what we know about factorials and exponentials, we can rewrite this as x over n plus 1. And as n goes to infinity, if we hold x fixed as n goes to infinity, this limit is equal to 0. That is always, obviously, less than 1, which means that our radius of convergence is infinite, and our interval of convergence is negative infinity to infinity. So now we see that this thing, the series, converges to some value for every number in negative infinity to infinity. So our task is to figure out, does it actually converge to e to the x? So we need to look at the error. So we need to look at r sub n of x, which we know is equal to the n plus first derivative at some value c over n plus 1 factorial times x to the n plus 1, where c is between our center, which is 0, and x. We know that the n plus first derivative is just e to the x, so this is going to be e to the c over n plus 1 factorial times x to the n plus 1. Because e to the x is an increasing function, we know that e to the c has to be less than or equal to e to the absolute value of x for all c between x and 0. Doesn't matter if x is a negative number or a positive number, this is going to be the case. So we can then write this as r to the n of x. We're going to throw an absolute value around that so that we can use positive values of x here. This is going to be less than or equal to e to the absolute value of x over n plus 1 factorial times x to the n plus 1 factorial, or no factorial on that. Remember, we want to examine the limit as n goes to infinity of these errors. And so that's going to be less than or equal to the limit as n goes to infinity of e to the absolute value of x times x to the n plus 1 over n plus 1 factorial. Since the first part of that has no n's in it, we can pull it out to the front. We get e to the absolute value of x times the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. This limit is something we've seen before. We know that x to the n grows much more slowly than n plus 1, or x to the n plus 1 grows much more slowly than n plus 1 factorial, which means that this limit is equal to 0. So our entire limit is 0. So we now know that for all x values, the limit as n goes to infinity of the remainder of the x is equal to 0, which means that e to the x is going to equal the sum from n equals 0 to infinity of x to the n over n factorial for all x that are real numbers. Let's walk through the same process for the function f of x equals sine x, again centered at 0. So if we do this, we know that f of 0 is going to be 0. We know that f prime of x is the cosine of x, which means that f prime of 0 is 1. F double prime of x is the negative sine of x, so that f double prime of 0 is 0. F triple prime of x is the negative cosine of x, so that f triple prime of 0 is negative 1. The fourth derivative of f is going to be positive sine x. We're back to where we began, so the fourth derivative at 0 is 0. So we can see here that we're getting these alternating values of 1, 0, negative 1, 0, and that cycle is going to repeat. So when we write our Taylor polynomial, right, we know that in general that is going to be f to the n, or f to the n, the nth derivative at our center a over n factorial times x minus a to the n. So if we start filling in what we know, we're going to have f to the n of 0 over n factorial times x to the n. But we have to notice that our series exists only for odd powers. Every other term disappears. So the way we write an odd power or an odd number is as 2n plus 1. So we're going to replace all of our n's with 2n plus 1 so that we are only counting terms where our coefficient is not 0. So we'll have x to the 2n plus 1, and then we'll divide by 2n plus 1 factorial. And then we're going to alternate, and the first term of our series is a positive 1. So that means that we're going to start with negative 1 to the n power, because if n starts at 0, negative 1 to the 0 power will give us a positive term. And so we can see that we do in fact get the sum from n equals 0. Once again, I used n instead of k. I'm not really sure why, of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So now let's look at what radius of convergence this might be useful for us on. So we're going to examine now the limit as n goes to infinity of the absolute value of negative 1 to the n plus 1 times x to the 2. I'm replacing all of my n's by n plus 1 now for my ratio test. So I get 2 times n plus 1 factorial. I'm going to multiply by the reciprocal of the nth term, which is going to be 2n plus 1 factorial, and negative 1 to the n, x to the 2n plus 1. Okay, the negative ones don't matter because of the absolute values, so we can kind of ignore those. And when we multiply some things out here, we get x to the 2n plus 3 over x to the 2n plus 1. I'm moving my terms around just so I can see more easily how this is going to simplify. And then I have 2n plus 1 factorial over 2n plus 3 factorial. All right, once again, we'll use what we know about factorial and exponents to simplify this. So we get x squared when we subtract the exponents, and then we get 1 over 2n plus 3 times 2n plus 2, because all the rest of the terms will cancel with the terms in the numerator. And that is just the absolute value of x squared times the limit as n goes to infinity of 1 over 2n plus 3 times 2n plus 2, but that limit is 0. So x squared times that was still 0, which means that once again, our radius of convergence is infinite. And we see that this converges over the interval negative infinity to infinity. So our series converges over that interval. And once again, we need to now ask, what is the limit as n goes to infinity of our error or remainder terms? If that goes to 0, then we'll know not only does the series converge everywhere, but that it converges exactly to the value sine of x. So let's inspect these remainders. So r sub n of x, the formula for that is going to be f to the n plus first derivative of f divided by c, or at c, divided by n plus 1 factorial times x to the n. We don't need x minus a here, or x to the n plus 1, because our a value is 0. We're doing a Maclaurin series at 0. But we know that for f of x equals sine of x, the n plus first derivative at any value c is always less than or equal to 1. Always. Because sine's derivatives are either sine, cosine, negative sine, or negative cosine, and the biggest any of those ever gets is 1. So we know that r sub n of x then is less than or equal to 1 over n plus 1 factorial times x to the n plus 1. And if we look at the limit as n goes to infinity of our error or our remainder, we know that that's less than or equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. Again, this is a familiar limit. We have a function on the top that's growing, but growing much more slowly than the one in the bottom, which means that this limit is 0. So we know that sine of x, the Taylor series we came up with, was the sum from, we'll go back to k equals 0 to infinity of negative 1 to the k, 2 to the k plus 1 over 2k plus 1 factorial. We saw that that converged for all real x, and we just showed, because the limit of the error pieces is 0, that this is exactly equal to the sine of x for all real numbers x. All right, we're going to stay with trig functions now and do the very same thing for cosine of x. So we have f of x equals cosine of x, so that f of 0 is 1. F prime of x is going to be the negative sine of x, so that f prime of 0 is 0. The second derivative is the negative cosine of x, so we get negative 1 for f double prime of 0. The third derivative is positive sine of x, so the third derivative at 0 is 0. And if we take the fourth derivative, we're going to get back to cosine where we started. and f of 0 is 1. So we can see something very similar to what we just saw with the sine function in that every other term is dropping out. We saw with our sine function that the even terms were 0. Here we can see that the odd terms are 0. So in other words, in this one, instead of using 2k plus 1, we're going to do something different. So once again, we'll start with the notion that our Taylor series looks like the sum from n equals 0 to infinity of the nth derivative at a over n factorial. I keep wanting to put in n plus 1, but that's completely wrong. And then x to the n, or x minus a to the n. But our a is 0. So we're going to have this f to the n of a over n factorial times x to the n. But because we need every other term to drop out, in other words, we need to keep the even terms and drop out the odd terms, we're going to change this up. We're going to let this be the sum from n equals 0 to infinity of something times x to the 2n over 2n factorial. And all we have to figure out is what is the something? What is that piece there? Well, we know that's going to be the thing that makes it alternate. So we're going to have -1. Then we have to ask ourselves, what exponent do I need on that? What exponent do I need on that? And so this starts positive. So if we start with just n there, we will flip from positive to negative, which is exactly the behavior that we want. So now we have our Taylor series, or our Maclaurin series, more specifically, for cosine of x. So let's examine this and see if we can find our radius of or interval of convergence. We're going to examine the limit as n goes to infinity of the absolute value of -1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial times 2n factorial all over -1 to the n x to the 2n. And just like we saw before, the negative ones, because of the absolute values, don't matter here. So we end up with the absolute value of x to the 2n plus 2 over x to the 2n times 2n factorial over 2n plus 2 factorial, which is the absolute value of x squared. We can move that to the outside because it has no n's in it, doesn't impact the limit, times the limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. Those are the only two terms that are left over when we cancel all the rest of the pieces of our factorial. And that is, well, this limit here is 0 as n goes to infinity, so the whole thing is 0, which means that our radius of convergence is once again infinity, and our interval of convergence is -infinity to infinity. Now, you should have some intuition here about what happens next in terms of whether or not this converges to the actual value of cosine. It's probably going to behave similarly to the sine. So we're going to look at the limit as n goes to infinity of our remainder, or our error. So that is going to equal the limit as n goes to infinity of the n plus first derivative at some value of c over n plus 1 factorial times x to the n plus 1. But just like for sine, the n plus first derivative of c for any value of c is less than or equal to 1, because cosine's derivatives are sine, negative cosine, positive cosine, as you cycle through for different values of n. So we can then say that this is less than or equal to the limit as n goes to infinity of 1 over n plus 1 factorial, n plus 1, times x to the n plus 1. And again, we're in that case where we have a function. Both of them are growing, but n plus 1 grows much faster. And so we see that this limit is 0, which means that for all x, for all real numbers, we know that the cosine of x is exactly equal to the sum from k equals 0 to infinity of negative 1 to the k, x to the 2k, all over 2k factorial. All right, we're going to move away from trig functions, and we're going to look now at f of x equals 1 over 1 minus x. This one shouldn't seem too unfamiliar. At this point, f of 0 is then 1. Let's start looking at some derivatives. So f prime of x is going to be 1 over 1 minus x squared. So we're using the power rule as well as the chain rule to make sure that this is positive. And then f prime of 0 is going to be 1. If we repeat that for the second derivative, we're going to get 2 over 1 minus x cubed. And f double prime of 0 is going to be 2. We can keep going until we start to see the pattern. Here we're going to get 6 over 1 minus x to the 4th, so that f triple prime of 0 is 6. We'll do one more, and then I'll feel pretty certain we have a pattern going here. So this is 24 over 1 minus x to the 5th. F to the 4th of 0 is 24. So what we're seeing here is that f to the n of x looks like n factorial over 1 minus x to the n plus 1, and that f to the n, this is nth derivative, not nth power, of 0 is then going to be n factorial. When we put that into our power series formula, or Taylor series formula, the sum from n equals 0 to infinity of f to the n of a over n factorial times x minus a to the n. We're using a of 0 here, so we're going to have the sum from n equals 0 to infinity of f to the n of 0 over n factorial times x to the n. Well, plugging in what we just found for the nth derivative at 0, we get n factorial over n factorial times x to the n, which is just the geometric series, the sum from n equals 0 to infinity of x to the n. This is geometric, and our R value is, well, it's x here, which means we know any geometric sequence converges when R is less than 1. So we're going to converge when x is less than 1. When x is less than 1. And if x equals 1 or negative 1, this is just a series of ones that won't converge. So we don't have to worry about the endpoint. So our interval of convergence then is negative 1 to 1. And now we have to look at, does the series actually converge to the function f of x equals 1 over 1 minus x? And to answer that, we're again going to look at our remainders. And in particular, we're going to look at the limit as n goes to infinity of the remainder. But let's come up with an expression for the remainder. We're going to use a slightly different formulation this time because we have a geometric series. Well, the remainder is always equal to the function minus the sum up until n. So we'll go k equals 0 to n of x to the k. This is the nth partial sum for a geometric series. We have a formula for that. So the remainder here is going to be f of x, that's our 1 over 1 minus x, minus the nth partial sum, but that's just 1 minus x to the n over 1 minus x. All right, this is the formula for the nth partial sum of a geometric series. So if we simplify that, we get that r sub n of x is x to the n over 1 minus x. Now we're going to take the limit as n goes to infinity of that expression. And we can actually take the limit as n goes to infinity, the absolute value. we can move the 1 over 1 minus x to the outside. It has no ends in it, so it's not affected by the fact that we're taking this limit. Then we just have this guy. But we have to remember here that we're on the interval -1 to 1. X is less than 1, which means as I raise x to bigger and bigger powers, that limit goes to 0. So what we see is that if the absolute value of x is less than 1, then the limit as n goes to infinity of our remainder terms is 0, which means that for values of x that are less than 1, it is the case that 1 over 1 minus x, that function, is exactly equal to the sum from n equals 0 to infinity of x to the n. It's not going to be the case for values outside of that interval, but otherwise, when we're within that interval, the function is exactly equal to its Maclaurin series. All right, let's examine a logarithmic function. So we're going to take a look at f of x equals the natural log of 1 plus x, which tells us that f of 0 is the natural log of 1, which is 0. If we take our first derivative, we get 1 over 1 plus x, so that the first derivative at 0 is 1. If we take our second derivative, we're going to get -1 over 1 plus x squared. And f prime of 0 is then going to be -1. F triple prime, taking the third derivative, we're going to get +2 over 1 plus x to the third. So f, this should have been a double prime, f, the third derivative is +2. And if we look at the fourth derivative, here we're going to get -6 over 1 plus x to the fourth. And again, that's going to be just -6 at 0. So we can start to see here that if we look at the nth derivative, first of all, they alternate. When n is 1, we get positive. When n is 2, we get negative. So we have a term that looks like -1 to the n plus 1. And then the numerator looks like n minus 1 factorial. And then we're going to divide that by 1 plus x to the n, so that the nth derivative at 0 is just going to be -1 to the n plus 1 times n minus 1 factorial. Now, a couple of things. First of all, notice that our f of 0 is 0, which means that we don't need that term in our series. Also notice that here we have an n minus 1 term, which means if we start off with n equals 0, we're taking -1 factorial, and that doesn't make any sense. So look at that. We already have it started here. We've got the sum from 1 to infinity. We're going to start at 1 because our 0 term doesn't exist. We have -1 to the n plus 1, and then we have n minus 1 factorial. That's for the derivative at 0. Then we're going to divide by n factorial because this is a Taylor or Maclaurin series, and then we're going to multiply by x minus a to the n, so we get x to the n here since a is equal to 0. And we can tidy that up, and we do in fact see that our series looks like the sum from n equals 1 to infinity of -1 to the n plus 1. N minus 1 factorial divided by n factorial is just, it gives us an n in the bottom, and we get an x to the n term. Let's figure out where this thing converges. So we're going to look at the limit as n goes to infinity of the absolute value. We know we can leave the -1 term out because of the absolute value, so we're going to get x to the n plus 1 over n plus 1 times n over x to the n, which gives us the limit as n goes to infinity of the absolute value of x times n over n plus 1, which is equal to the absolute value of x, since n over n plus 1 goes to 1. Well, we know that that's going to converge. Our radius of convergence is then going to equal 1. So our interval of convergence is possibly -1 to 1, but we want to check our endpoints. So to do that, let's check x equals -1 first. If we plug in -1, we get the sum from n equals 1 to infinity of -1 to the n plus 1 times -1 to the n all over n factorial. Well, that's the same thing as the sum from n equals 1 to infinity of -1 to the 2n plus 1 over n factorial. This right here, -1 to the 2n plus 1, we're raising -1 to an odd power. 2n plus 1 is always an odd number. So this is going to be the sum. You know what? I put a factorial in here, but that does not belong in there. So let's take it out. Those don't belong in there. We just have an n in the denominator. So now we have the sum of -1 over n, which we know is the harmonic series which diverges. So this thing does in fact diverge at -1. Let's see if anything different happens at +1. At x equals +1, we're going to get the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 to the n over n, which is just going to be our alternating harmonic series. So this one does in fact converge. So we're going to correct our interval. It's actually going to be from -1. We're going to include +1. All right, our last order of business is to see, does this thing converge to its designated function on its entire interval? So here we have to look at the limit as n goes to infinity of r sub n, or the absolute value of r sub n of x. But we know that this is an alternating series, which means that r sub n of x is just equal to, or the absolute value of that is equal to is less than or equal to the absolute value of the n plus first term. So this is going to be less than or equal to the n plus first term, which looks like, or the absolute value of the n plus first term. So we can take out the -1 again, and we just get x to the n plus 1 over n plus 1. And because we are on the interval, we know that the absolute value of x is less than 1. This term, as n gets really big, this term actually goes to 0. So our entire limit must be going to 0 because our denominator is getting bigger and bigger. So we're getting smaller and smaller numbers divided by bigger and bigger numbers. That limit is 0. What does that tell us? That tells us that for all values of x that are in our interval, I don't know why I wrote a negative infinity there. That should have been a -1. There are in our interval from -1 to 1. It is the case that the natural log of 1 plus x is equal to the sum from n equals 1 to infinity of -1 to the n plus 1 times x to the n over n. All right, we've got one last example. Here we're going to look at the function f of x equals inverse tangent of x. And we're going to establish its Maclaurin series, but we're going to do this slightly differently than any of the others. We're going to notice that the derivative of this function is 1 over 1 plus x squared, which actually means then that the antiderivative of 1 over 1 plus x squared dx is equal to the inverse tangent of x. How is that helpful? Well, we know that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n for absolute value of x less than 1. This tells us that 1 over 1 minus negative x squared is going to be the sum from n equals 0 to infinity of negative x squared to the n by using composition of functions to do that. Well, that is going to equal the sum from n equals 0 to infinity of negative 1 to the n x to the 2n. So now what we know is that the antiderivative of 1 over 1 plus x squared must be the same thing as the antiderivative of this series with respect to x. And because of the way that antiderivatives work, we can move the sum to the outside. Because the negative 1 to the n part doesn't have any x's in it, we can move that out to the front as well, and we get the sum from n equals 0 to infinity of negative 1 to the n times the antiderivative of x to the 2n dx. That's a straightforward power rule for antiderivatives, so we get the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1. Plus we've got some constant that we're going to add on here. So now we have to think about inverse tangent of 0. Inverse tangent of 0, if we use this here, that's got to be this sum then from n equals 0 to infinity of negative 1 to the n times 0, 0 plus c. But inverse tangent of 0 is 0. So we get that our c value is 0. So now we know that inverse tangent of x can be written as this series. Negative 1 to the n, x to the 2n plus 1, all over 2n plus 1. And we need to know our interval of convergence. So we'll examine now the limit as n goes to infinity of the absolute value of x to the 2n plus 1, or x to the 2 times n plus 1 over 2 times n plus 1 times 2n plus 1 over x to the 2n plus 1. And we're going to see that's the limit as n goes to infinity of the absolute value of x squared times 2n plus 1 over 2n plus 3. Well, the limit of the pieces that has the n have the limit of this is 1. So our limit here is equal to the absolute value of x squared. We want that less than 1, which has the same thing as saying that the absolute value of x is less than 1. So for sure, our interval has to be negative 1 to 1, like it was for our original sequence or series. Now let's look at our endpoints. If we plug x equals negative 1 into our series, we get the sum from n equals 0 to infinity of negative 1 to the n times x, times negative 1 to the 2n plus 1 all over 2n plus 1. So that's negative n to the 3n plus 1 over 2n plus 1. So since our exponent is 3n plus 1, sometimes that's an odd number, like when n is 0. Sometimes that's an even number, like when n is 1. So in other words, this alternates. Even though the exponent just isn't straight up n, this is an alternating series. And so it looks like the alternating harmonic series, and hence it's going to converge this is going to converge in comparison to the alternating harmonic series. So this converges at -1. Similarly, if we look at x equals 1, we get the sum from n equals 0 to infinity of -1 to the n over 2n plus 1, which by the exact same logic, it's an alternating harmonic series is going to converge. So what we actually found out is that our interval of convergence is -1 to 1. All right, so now our job is to check to see if we converge to tangent on this entire interval. So we're going to look at the absolute value of the remainder. Because it's an alternating series, we know that's less than or equal to the absolute value of the n plus first term. So our limit as n goes to infinity of r sub n of x is less than or equal to the limit as n goes to infinity of the absolute value of x to the 2n plus 1 over 2n plus 1. But again, remember we're on this interval, which means our x values are smaller than 1, which means that as n goes to infinity, the top is going to 0, the bottom's going to infinity. So we have numbers that are getting smaller and smaller, being divided by numbers that are getting bigger and bigger. So that limit is 0. So we now know that for all x on our interval, it is the case that the inverse tangent of x is exactly equal to the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1, all over 2n plus 1. All right, let's wrap this up. This is a very long one, but let's wrap this up with a summary of the 6 Taylor series that we saw here. We saw that e to the x could be written as a series involving x to the k over k factorial, and then that equivalence worked for all real numbers. Similarly, sine of x and cosine of x, their Taylor series, are valid across all real numbers. The function 1 over 1 minus x is equivalent to the geometric series x to the k, but it only converges on -1 to 1, and that is where it's exactly equal to its function value. Natural log of 1 plus x, we get a slightly larger interval where you get to include 1 this time and converge and equal the function over that whole interval. And then the inverse tangent of x is equal to its Taylor series expansion across the interval, the closed interval from -1 to 1.